Now in the earlier lecture, we already learned that how we can calculate the value of this Cdyn for the, we can say, tall buildings. Now in this lecture, we should learn that if we are having a situation or a problem where we have to calculate the Cdyn, that is a dynamic coefficient for these kind of head frame structures, we can say, or we can say the mast supporting the head frame. So technically, in engineering language, we say it as a mast only, and that is usually installed in the, we can say, stadiums itself. So just to give you a brief example here, this is the Gaba Stadium in the Queensland. So here you can see this the practical we can say mast supporting the head frame structure, head frame. So this is on basically the LED lights are fixed on the top, and this is basically the mast which needs to be designed for the wind load. Now we shall be having a practical example also in the for the analysis also, but just to help you calculate the value of the Cdyn, we do need to understand the technical concept first. So let us suppose the design wind speed that we are having a 60 meter per second. Let us assume that the first mode natural frequency, and first mode natural frequency can be calculated by the softwares also. So either you are using the Space Gauss software, or you are using the ETABS, or you are using the SAP 2000 software. All of those softwares can help us to calculate the fundamental natural frequency of the structure. But we have to model the the upper frames and upper head frames, and we have to model the mass also of the light. Only then we shall be getting the correct frequency of the structure. After that, when we are let us assume the height of this tower is 100 meters. Height of this, we can say, mast also, or some of the height of the head frame and ancillaries. So this H effective is basically this particular height here, that is from this point to this point. This is basically the H effective here. After that, if we are talking about the turbulence intensity IZ. So in here, if you're talking about turbulence intensity, let us assume that we are talking about the height H as 100 meters itself, and let us assume we are considering it as terrain category 2. So the turbulence intensity here for this particular assumption is 0.131. So we can enter the value here as 0.131. So after that, peak factor GV, that is fixed value, that is G.4 here itself. And after that, if you're talking about the average width of the head frame, so average width of the head frame is basically this dimension here, and this is also usually supplied by the, we can say, whomsoever is designing the lighting arrangement of the stadiums. They do say that, okay, we have to install, let us say, 40 number of lights or 30 number of lights. On the basis of that, we do get this input from them itself. So after that, let us assume it is 20 meters. After that, we can calculate the value of the LH also. So LH can be a measure of integral turbulence length scale at height h. So this can be calculated as 151.154. After that, the value of the GR, that is peak factor for resonant response, that is basically 1.2 plus 2 log base C, 600 and multiplied with the NA, that is the natural frequency. So after that, we can calculate the size reduction factor also as dash with this particular equation. We have already discussed in detail. So NA is basically the fundamental frequency, H effective is the height of the head frame, GV that we have already calculated above as P factor for upwind velocity fluctuations, and IH that also we have calculated as the we can say the turbulence intensity. So similarly, we do need to multiply this number also. So NA is again the natural frequency, B effective is the width. Again, this equation is repeated here, and that needs to be divided with the V design theta. So entering that, we do get the value of the size reduction factor as 0.396. So after that, if we're talking about the reduced frequency, that is non-dimensional. So N is basically NA into LH multiplied with 1 plus GV into IS divided by V design theta. So this value N comes out to be 2.367, and ET, the value we can say that comes out to be 0.051 by entering the values in this particular equation. So N, whatever we are calculating here, that can be simply entered here to find out the value of the ET. Now, assuming that the structure that we are having is basically steel structure, assuming, so we can enter it the we can say ratio of structural damping to critical damping here is 0.015. So that we can enter here. And after that, the final value, that is the value of the Cdyn that can be calculated here is 1.28. So IH we have already calculated above, GV again, GR also we have calculated, S dash also side reduction factor, ET also we have calculated, and that needs to be divided with 1 plus 2 into GV into IH. So Cdyn at the top level comes out to be, we can say, approximately 1.28. Now let us just understand the practical considerations also. So if as an engineer you are having an problem statement that you do need to design this particular mast supporting structure, you do need to design the foundations also, and you do need to ensure that this tower stands or remains intact at the time of the extreme winds. So how we can do that? So, there's an excellent software by Australian engineers themselves. So this is an Australian software that is Checkpole. So let us just, have a practical, we can say, statement here. Let us assume that we are having the, we can say, concrete mast itself, because we are talking about a lot of height here. Let us assume, and there are various vendors in Australia which do provides the, we can say, the monopole, because we cannot do the shuttering and construct it at the site. We have to we can say make them as a precast member, and we can fix them at the site if we are talking about the concrete monopole structure. So Rockla is one of the vendor, and Gridcom is also a supplier, and Transfield is also a supplier. Assuming we are right now talking about the Rockla, and assuming it is a concrete, we can say, pole here. Shape we assumed it as circular, and segments we have assumed it here as 5. So after that, access system is also assumed here. Access system is basically, we may have to go up also. So for that, usually the steps or small staircase is also provided. So why we have to consider that? Because that also puts the horizontal wind load on the main structure. So that is why either it is small steps, or if we can remove them also. So if we are considering the step pegs, then the software shall calculate the wind load also for the contributory area of the pegs, or we can say step pegs. So we have assumed here is divided into 5 parts. So the first part here we can assume it here as the one that is, we can say, S05, and after that it is S04, S03, S02, and S01. So S05 we have considered as 7 meter, so that is considered as an embedment depth itself. After that, the fourth part here, that is assumed as 9 meter, that is from this point to this point. So the, we can say, the strength, so we can say here that the strength of this part is considered 65 MPa, because right now we're talking about the concrete cross section, and this is a hollow cross section. After that, again we are considering as 10 meter height, and after that again we are considering as 12 meter, and on the top it is considered as 4 meter. So right now we are talking about 10 meter plus 9, 19, 29, 31, and 35 meter height. So 35 meter is the height of the, we can say, mast above, and 7 meter is the height below. So after that, the software do have a capacity to calculate the, or to help us have the exact location, and as per the exact location, it can automatically calculate all the various parameters as per the AS1170 part 2. So we can enter it as here as we do need to consider the AS-NZS 2021. CSA S37 is basically Canadian standard, EN40 is the European standard, LRFT LTS is basically American standard, and TIA that we have already discussed is that Telecom Industrial Association, that is an universally recognized standard. So yeah, so after that we do need to consider the Australian standards. Just a minute. So we can consider as an importance level 2, and we can consider design life also as 50 years. We have selected the code as AS-NZS1170.2 2021. So region that is automatically selected as B1, And according to that, we can select the serviceability VR also and ultimate VR also, that has been considered as 57. So after that, we can either have we can say different values for, we can say MD, that is the for different directions, or what we can do is that we can assume it as one also. So by considering it as a density sensitive structure, we can have a different values of the wind speed and different values of wind pressure from different sides. And after that, let us just check that what exactly are the different kind of terrain categories from different we can say directions. So although we can say that it is a very crowded area because the stadium is inside the city, so in majority of the areas we are talking about a terrain category 3 itself. So that also it has detected, but we can again detect it that with the help of this check pull software. So I must say that it is an excellent software if we are going ahead with the design of the, we can say, monopoles, also transmission towers, also as per the Australian standards. So it has detected we can say a terrain category 3 from different directions. And after that, if we are talking about the MS has been assumed as 1, and MT, that is topography factor, that also has been assumed as 1 because we are right now talking about the horizontal surface only. So after that, if we are talking about the loading, so loading, if we are talking about the loading on the these kind of mast structures, we are talking about the head frame only. That is, we are talking about the large group of lights on the top of the mast. So here we have assumed it as this particular mast is having 16 number of lights. So that is why 16 number of headlights has been assumed here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And the angle of these lights has been assumed as 315 degree. So, if we see this in the, we can say the 3D view, that also we shall see. But, it has been assumed that this whole arrangement is in, uh, we can say 315-degree angle. And that is also a practical thing also because we have to, drop the light on the bottom. So here also you can see that this particular, tower supporting, mast supporting this head frame, there is this particular angle. So this angle has been assumed as 315 degree, or we can say 45 degree clockwise from the vertical. So that has been assumed, and as per the location, we have made these custom lights, and on the basis of that, it shall calculate the wind load on this particular head frame also. So after that, we have assumed we can say light array also. So here itself we have entered here 315 degree, and height and width has been assumed as 6 meters and 5 meter, and depth has been assumed as 600 mm. So all these things have been entered here as per the assumption, so that the software can calculate the loading because of these additional elements. So we can just go to the analysis tab here. So this is our final, we can say, mast supporting the head frame, and let us just see this particular head frame structure here. So this is basically the 3D view, we can say also, of the mast supporting the head frame structure. So we can just do the first of all the analysis here. So here we can see that the first more natural frequency that the software has calculated is 0.8412, and that is less than 1 hertz. So we have to calculate the value of the Cdyn also, that is the dynamic coefficient also. And let us just close this and check the results here. So natural frequency has been calculated 0.8412. And if we are talking about the, let us just say first of all, if we are talking about the dynamic coefficient Cdyn, so this value has been calculated as 1.1882 on the top and 1.0679 at the base level. So this Cdyn value has been changing as per the heights. So it has been varying from 1.067 to 1.188. Second step, if we are talking about the bending moment at the base, so obviously bending moment diagram shall be something like this. And after that, if we are talking about the bending moment here, the bending moment at the base is 2367 kilonewton meter at the base, and it is obviously reducing to, we can say, 91.52 kilonewton meter at this particular level. So we can say that because of this head frame management. Yeah, because of this head frame management, the bending moment at this particular level is 91.52, which again is increasing to, we can say, 2367 because of the cross-sectional area of this particular mast supporting structure itself. After that, if we are talking about the torsion, so torsion is very less for 14.32. And if you're talking about the shear value shall be substantially high, that is 100.54 kilonewton at the base. Now, we have selected the different, we can say, values of the, we can say, directional wind speed. So what we can do here is that, you know, for MD, what we can do is that we can simply take this value as 1, because right now we are not talking about the conservative, or we can say actual approach. Let us just take it as 1, so that we shall be able to understand the results correctly, because otherwise it shall be giving the results with different wind directions. So although we can do that in the practical, but just as a theoretical understanding, let us just go with the simple approach first, so that we can understand. So in here, if we're talking about the, we were talking about the shear force. So shear force here was basically 125.98 kilonewton at the bottom and 31.2 kilonewton at the top. After that, if you're talking about the axial forces, so axial forces is basically 349 kilonewton is basically the axial force at the bottom, and 0. We can say 24 kilonewton is at the top. Similarly, we can check the rotation also. That is, rotation is coming approximately, we can say, 1.39 degree. After that, the important parameter is this particular parameter, that is a deflection. So deflection here, we can see here that at the top, 502 mm deflection is coming on the top. That is, it is going as high as, on the right or on the left as per the wind direction by 502 mm. So we are talking about the very tall structure also, we're talking about the slender structure also, and we are talking about a wind sensitive structure also. So we cannot say that we shall be dealing with a deflection of only 10 mm or 15 mm. Obviously we shall be dealing with a high deflection, but the parameter is that, there are two concepts here. One concept is that because of this particular displacement, we have to consider the secondary effect, that is P delta analysis. The second concept is that we have to ensure that this deflection has to be within some permissible limit. It is not that we can allow any magnitude of displacement at the, or deflection at the top. After the utilization, that is the concrete section utilization at the bottom is 70%, and on the top it is 20%. Cdyn value that we have already discussed, that it is varying from 1.083 to 1.212. After that, wind speed, V side beta. So obviously it varies with the height of the structure. So it is like 47.3 meter per second at the bottom for northeast direction, and 60.28 meter per second at the top for the northwest direction. Wind pressure value is basically 1.3429 kilonewton at the base level, and it is going as high as 2.1802 at the top level. Now drag factor CD is basically 1.2. Now you need to understand that, if you're talking about a drag factor for circular cross section, we shall be discussing in the detail in a separate lecture. But as per the different cross section, whether it is circular, whether it is octagonal, whether it is any other cross section, the value of the drag factor changes, and this is given in the code itself. So as per the code, for circular cross section, the value of CD is 1.2, and that has been considered here also. So these are, the different, we can say, the action effect that we have, that we can see here. And if we can also change the load cases also. So, our maximum optimization, sorry, maximum utilization here is with 1.2 time, we can say, permanent load plus wind load. So in here, we are getting the governing actions, that is for with 70.34 utilization. So we can do the design also here, and the software shall, give us the results also. So at the base, we are getting the maximum utilization of 70.34%. So here also, it has checked as per the, we can say, AS3600. And as this was a Rockpool user guide, so we can say that it was a Rockpool, we can say, standard section. So they do provide us the user guide which has a capacity for different cross sections. So as per the, the design manual itself by the vendor, we can say, or by the supplier, that is Rockla or Rockpool. So the moment capacity is basically 4221 kilonewton meter. Torsion capacity here is 727. But now the moment that is coming at the base is 2969 kilonewton against the capacity of 4221. So that is also safe. Torsion capacity, torsion that is coming is 10.64, but torsion capacity is 727. And that is obviously multiplied with the strength reduction factor also. So it is 1.46%. Shear capacity is also like 125 kN is the shear capacity against 125 kN is the shear force against the capacity of 639 kilonewton. So that is also safe. Compression capacity as per AS 3600 section 10.6.2.2. The formula that is given is phi multiplied with alpha 1 multiplied with F dash C multiplied with the gross cross sectional area, which when multiplied gives us the value of 12535 kN against the actual capacity, against the actual force of only 349 kilonewton. So with this, we can say that our section is safe, and we can use that. So AG, that is a gross cross sectional area for this, size is 399,278, and that has been considered here also. So similarly, we can check the other sections also. So if we are talking about the section on the top, the section on the top is having the, cross section area 202473. The capacity is, as per the Rockpool user guide, is 495 against the bending moment that is coming is only 100.3. So similarly, we can, check the member with for moment, torsion, shear capacity, and compression cross section capacity. So if required, we can take out the document also, and we can print out this document, and we can submit that in our analysis. So although it is a summary document, similarly the software do help us to calculate the, or to have the detailed document also. So this detailed document usually comes out to be 200 or 300 pages minimum, because it do checks for each and every load case, it do checks for each and every load combination, for each and every cross section also, for each and every level also. So I won't be going into detail in this particular document, because that is a standard thing that we have already discussed right now, that when we were discussing here for each and every cross section, we can check the capacity that the vendor is providing as per the Rockpool user guide, and we can check the bending moment, or we can say torsion, shear, axial forces that are coming on this particular member. So on the basis of that, we can check that whether the section that we are dealing with is safe or not. So that was the practical example of how we can calculate that. Now let us just do a simple, we can say, modification. And let us just try to model this particular, we can say, mast at the beach itself. I mean, just as a we can say trial, we can say. So let us just try to change the location, and then check with the different wind loads. So what we can do in the software is that we can just simply click on the site and we can just simply double click on the required location. So on the basis of that, it shall automatically integrate with the, we can say, Google Maps, and then automatically help us to calculate the terrain categories also, the regional wind speed also. And this software checkwind, they are also, have a software called checkwind, which is integrated with space gauss also. So that is also a very good integration, I must say, because the majority of the time of the structural engineers in Australia is, we can say, utilized in calculating the wind loads. And if there is a software which help us, uh, saving the time or saving the hours, or we can say the saving the engineering cost, that shall help us a lot. So this is the required location that we have assumed, and on the basis of that, we can just simply see here that the terrain categories have been assumed here as one from this particular side, but from the left hand side we can see some buildings here. So that is why from this particular side, the software has considered terrain category 2. Here also it is assumed as terrain category 2, it is assumed as terrain category 2, but from the right it is assumed as terrain category 1. So that is the approach. And here also you can see the topography factor is also there. So the software automatically calculate the topography factor also. Okay, so after that we can just simply do the analysis again. So we can see here that the bending moment also is drastically increased to 4299.62 kilonewton. And if we are talking about the, we can say, torsion, the torsion is not that a problem when we're dealing with the mast structures. Shear has also increased, axial force has also a little bit increased, rotation has also significantly increased. So this deflection on the top was only 500 mm approx in the earlier location, but now it is 758 mm because the wind load has increased. Utilization, here you can see that now the section is not passing in the design, like 101.86 percentage is there at the bottom. So we have to increase the diameter. So Cdyn value, like it was 1.2383. Wind speed has also been must also been increased. Yeah, so now it has increased to 70.24 meter per second, obviously from 10 category 1. So wind pressure also must be significantly increased. So this is also increased to 2.9602 kPa. Drag factor shall be same as 1.2. So we can check the design also. So we can just left click on this particular calculator here, we can say. And as per the the Rockpole user guide, the bending moment capacity is 4221, but the bending moment that is coming is 4299. So it is straight away failing in the bending moment itself. So what we can do is that we can just simply go to the structure and change the, or we can say increase the thickness, or we can say increase the diameter also, so that the the capacity of the, we can say, the cross section increases. So I hope the concept is now clear to that how you can calculate that, and you can check the other part also, like what exactly are the openings that are provided, and what exactly are the arms, and what exactly is the connection arrangement also. So that was just a basic introduction to how you can design the mast supporting headboard structure. So you can go through the Excel file again, and you do need to understand all the formulas and all the we can say the concepts that are given as per the code. There may be a case, although in my experience I have not faced it, but there may be a case where we might be having two levels of this mast, head frame. So this two level of head frame maybe having some gap also at the center. So H1 and H2. So H effective shall be H1 plus H2, and B effective shall be 0.5 times B1 plus B2. So that is the only difference. So I hope this calculation of Cdyn for mast supporting head frame is not clear to you.